I'm founder and CTO at a company called Ambiq. We are an Austin-based company, although we're a worldwide company. We have offices in China and Singapore and Taiwan. And what we do is we build the world's most energy efficient chips. But what I want to talk about today is bringing a doctor, bringing a personal trainer to that risk. So that's something that is kind of a passion project of mine, and we're working hard to make happen at Ambiq. Okay, so central to this though is a problem we have, and that is that medicine is very, very expensive and it's very reactionary. Okay, so in 2016, something like 20%, 27% of total U.S. healthcare spending, that's $730 billion, was related to modifiable risk factors. What that means is these are risk factors that we can eliminate, that with changes in our behavior, we can get rid of it. So that's a whole bunch of savings and a whole lot more healthy years that we live to address it. It's things like high body mass index, it's high blood pressure, it's diabetes, dietary risks. These things are all things that are avoidable, and so the opportunity lies in this. The opportunity lies in this. We're all walking around with what is effectively a supercomputer on our wrist. Many of us are. And I use that term maybe a bit tongue-in-cheek, but the amount of compute horsepower that my watch has today is basically on par with early cell phones, and it's certainly on par with long ago data centers. So we have these incredibly powerful machines here that are increasingly capable. So that's something like 30% of US adults are walking around with a wearable today. And there's more than 150 million new wearables sold every year worldwide. So there's a huge and growing population of people walking around with these things on their wrists. And it's something that we at Ambiq are working to make happen. And what's exciting to me is I've seen the early customers that we have. We sell little microprocessors that go inside these devices, among other things. The early versions of them were basically pedometers. They were step counters, right? Go back and look at the early Fitbits. They were just step counters with a little flower that grows. Today, they're becoming all out, called consumer grade medical devices. You can do heart health tracking. So this device tells me my heart rate variability. It tells me, estimates my VO2 max. It is looking at my resting heart rate, all sorts of other things. It's tracking my sleep, which I find, by the way, is one of the most important health metrics that I've got. I go to CrossFit 5 times a week, and I'm obsessed with the exercise and performance tracking capabilities of this. So the VO2 max tracking, tracking how many calories I'm burning in a day, making sure that the macronutrients I'm eating in a given day are balanced and meeting that total. And then there's actually some really exciting work happening for more traditional medical companies. So think the Abbott's of the world. They have blood glucose tracking, lactate tracking patches that are minimally invasive, not invasive yet, but minimally invasive, and that's exciting. So we're seeing little bits of light here in what could be a really amazing opportunity to help us attack that problem from the previous slide. And the real vision though is this: it's not what we have today. The vision is I want that doctor and that personal trainer living on wrist. So the doctor should be able to tell you, hey, I've noticed that your heart health may be in jeopardy because you're not sleeping well these last few nights. I want you to go to bed at 10 o'clock for the next 3 nights. Let's get back on track. Your personal trainer should be looking at your blood glucose levels, should be saying, hey, I think that you've not eaten correctly for today. Let's amend that so we can get after the rest of the day. That same personal trainer on your wrist might say, hey, I've crafted a strength training program for you. Let's go do this guided workout today. And then actually one of the neural networks that our team is working on right now would be a Parkinson's detector. And so you can imagine that it's tracking your speech patterns, your movement patterns. The device says, hey, you know what, I flagged some concerning patterns. I'd like to go see a doctor before too long. Big opportunity there if we can get out ahead of these health problems before they become major. Then we save money, and more importantly, we live higher quality lives. And so it's clearly we're not there. It's not happening today. There's a variety of reasons, some of which excite me and are what we're going after, some of which are not unexciting, but important nonetheless. So the first of those is what I'll call the front end problem. It's difficult to sense many of the quantities that we want to sense. So I am building chips, and so I hear constantly about new sensors, and I hear about non-invasive blood glucose monitoring. That would be an amazing thing if someone could figure it out. For all the smoke that we've seen, there is yet to be any fire. We haven't seen anybody conquer that, at least in a commercial way. And there's a million other biosignals that we'd like to sense, and it can be really hard, especially if you say I'm going to do it from a wrist or from a ring, or I'm going to do it in a minimally invasive or non-invasive way. The second big problem is what I'm calling the backend problem. Let's say we magically collect all that data. We have to do something with it, right? You have to, it's difficult to take all this raw data that's been collected and make decisions based on it. I'm going to talk more about all of this in a second. And then these first two problems are exciting, right? The front end problem, the back end problem. These are technology problems that we're all working to solve. The last problem is one that actually doesn't excite me. It makes me upset and tired and all this, but it's the ecosystem problem. It's that even if we did solve all these technological problems, we lack a healthcare system that allows us to implement this effectively. So just as an example, if I go to my doctor, I can get all kinds of, I can get an X-ray, or I can get an MRI scan or whatever, and my health insurance will potentially cover it. If I go to that same doctor and said, hey, I'd like to avoid future health problems by going to the gym, insurance isn't going to cover that, right? That's a problem, right? Because that's actually a much cheaper and more effective remedy to this problem. And so I say that this problem doesn't excite me because it's not a technology problem. It's one that big organizations, big governments all need to get together and address. I think we can get there. I don't think it's anything compared to these first two challenges. But today, I don't want to focus on that. I want to focus on this middle problem, this backend problem. That's something that we at Ambiq are working to solve, and in fact are solving. Before I talk about that, though, I want to give you a bit more background on what Ambiq does. So I said earlier that I founded a company that put chips everywhere, and that was to put intelligence everywhere. In fact, that's in the name Ambiq. Ambiq means ambient IQ and ambient intelligence. And the idea is we're putting intelligence in the paint of the walls, the clothing that we wear, and the watches that we wear, on the livestock that we're raising, all with the goal of tracking it, understanding it, building those digital twins that we were just talking about, whatever. And to make all of that happen, these devices are largely mobile, and that means battery or power efficiency. So Ambiq is really focused on building the world's most energy efficient chips. We've done so using a circuit design platform that came out of my PhD work at the University of Michigan. And it's based on old technology called subthreshold circuit operation. This goes back to the 70s, the 1970s. And basic idea is this, for those of you that don't know. When we design typical digital circuits with the MOSFET today, we represent a digital 0 with 0 volts. We represent a digital 1 with a voltage that's much higher. And that voltage might be 1 volt, 1.2 volts, 0.8 volts, whatever. In any case, that voltage is above the turn-on voltage, the threshold voltage of the transistor. So transistors on, transistors off. I get a really strong one, and a really weak signal. In subthreshold operation, we never turn that transistor fully on. Okay, we never raise the voltage high enough to turn it on. And so we're swinging between 0 and 1 at a very low voltage. And to first order, this is interesting because energy is voltage squared. So I get a quadratic reduction in voltage. Sounds really simple, but people haven't been doing it, or at least not in a widespread way. And that's because of 3 problems that you can see on the lower left there. Namely, that we are exponentially sensitive or nearly exponentially sensitive to manufacturing variations, to process variations, to voltage fluctuations, to temperature variations. And so it turns out it's just really hard to design in this regime. And that's where we come in. We've got this 40 or 50 technology elements that all need to work together to overcome these problems. And we call that SPA. It sits at the digital level, the analog level, manufacturing test level, memory level, and even now at the software level. And the cool thing about it is it's a technology that we can use pretty much anywhere. We've at Ambiq chosen to use it on microprocessors, so microcontrollers in particular, but we can build inference engines, we can build data center based chips that are doing training or inference. We can build connectivity chips and sensing chips. So today, even engineering team is building some amazing delta signal ECs that are great for audio applications, all using sub-threshold circuits. So a lot of really cool applications for the product. And the coolest thing is, forget all the technology stuff. The most important and coolest thing is that we vastly outperform the competition from a power and consumption standpoint. You can just see a kind of an obfuscated comparison of us against our competitors in the lower right there. Smaller bar is better. It talks about how much power we use for every 1 megahertz of clock frequency on a chip for comparable parts. So we're getting a 4 to 8 to 10x advantage over the nearest competitors. For our customers, this is really valuable. Yeah, of course, they can extend battery life. Actually, the most exciting thing is they can add new functions. So as we're going to talk about in a second here, when we talk about AI and bringing that doctor and personal trainer to your wrist, in the same power budget that yesterday was a step counter, today they can build devices that do a whole lot more that are medical grade sensing devices. So what we sell today is a family of SoCs that we call Apollo. There are actually now four publicly announced generations of Apollo: Apollo 2, Apollo 3, Apollo 4. These are, I'll show a block diagram here in a second so you get a sense of what's inside, but with each generation of Apollo, we've added more functionality. So Apollo 3 generation had microprocessor, had all kinds of sensors, had Bluetooth radio. The Apollo 4 generation added in a GPU, added in a whole bunch of security functionality. We heard in the previous presentation about how important security is in the IoT. If you had told me 10 years ago that we were going to have a product with a GPU on board, I would have said you're crazy, but here we are. Moore's Law is a wonderful thing. And there's more to come. The cool thing that I commit to my customers is every year I'm going to give you something better than what they had last year. And so some of that is Moore's Law, right? Some of that is I've gone from 180 nanometers to 90 to 40 to 22. Some of it is architectural innovations and circuit innovations, but bottom line is we're going up and to the right. So we're going to have products that will constantly be faster, lower power, have more memory, more features. And that's exciting, especially when we consider that software and neural networks are growing at a very, very fast pace. I mean, the pace of development there is like, right? Weekly, we see new papers go up that kind of change what we thought was standard last week. So just to give you a snapshot of what we sell a lot of today. So if you were to break open any number of wearables you could buy at Target or Best Buy today, you would find Apollo 4 Plus. And I'm not going to walk you through this whole block diagram, but just to give you a sense of what's in it, there's a Cortex M4 microcontroller core in the upper left there that can run up to 192 megahertz. There's a whole bunch of memories on board. So we have non-volatile memory, actually MRAM, magnetic RAM on this chip. We have all kinds of SRAM. We have a BLE radio, a Bluetooth Low Energy radio. It's only a separate core, so it's a multi-core processor. As I mentioned before, there's a GPU. It's not just wearables, right? We have all kinds of other customers that have displays. There's tiny displays. We heard about user interfaces in the previous presentation. This is a critical one for us. There's a low power audio subsystem. So I think of microphones as just another sensor. So just like an accelerometer or an optical biosensor, microphone is just another interesting sensor input. Of course, what makes Apollo stand out is the power consumption. So mostly, of course, there's active mode where we're doing active compute. There's deep sleep mode where we're sitting there sleeping. Both matter in a world where we're doing more compute than not. It's really the compute power that ends up dominating. It depends on the applications, of course. But we have by far the lowest active power in the world. And as I said, that's something that's going to be improving moving forward. So now that I've talked a little bit about what Ambiq does, I want to go back to this backend problem. Remember, I'm assuming for the moment we've got a bunch of sensor data that we're getting on chip. We've got to do something useful with it. And so there's a couple of options in how we can do this. First, let's understand the data. So I was looking through our customers' wearables, and I was doing a rough estimate of how much data might be generating every second, every day. When you look at the microphone, you look at the inertial measurement unit, you look at the heart rate sensor, it all probably adds up to the order of 50 to 60 kilobytes of data per second. So that sounds pretty manageable, right? It's not that much data. but it starts to feel unwieldy when you go, well, that's 180 megabytes per hour. It's 4.3 gigabytes per day. So this device is sitting here capturing, let's call it over 4 gigabytes of data out in a day. So one option is I can send all that data up to the cloud. We can do processing there. We in fact are aware of customers doing this today, and it's a perfectly valid approach. The problem is that you're spending a whole lot of energy streaming. You've got a radio, maybe it's spending a good, well-optimized radio today is going to stream at about 10 milliwatts. So your 185 million or milliwatt hour battery is going to go dead in about 18 hours. You can't even make it through a day. I can't do sleep tracking if I can't make it through a day. So that's a no-go. Okay, we don't want to stream all the raw data to a server process. Now the other option is, well, let's bring the server processing local. Now I'm going to give you a ridiculous example here, but let's say we heard about ChatGPT in the previous talk. Let's say we wanted to build a large language model, or these large language models out to the endpoint. We'll run something like ChatGPT on my wrist. Well, even the relatively lighter weight models require tens of gigabytes of memory. You're looking at quadrillions of operations per inference, so sort of pet operations. And you're at least in a data center, you're looking at devices that have kilowatt hour or kilowatt power envelopes. That doesn't translate. I mean, clearly, this is a ridiculous example, but in a wearable, I've got maybe tens of megabytes of memory available to me. Yeah, I can put big NAND flash chips in there that even gigabytes of memory, but fast DRAM or SRAM like memory, you're looking at tens of megabytes. You're looking at maybe a compute capable of giga operations per second, so a billion operations per second, which is actually pretty damn big. And you're looking at power budgets around milliwatts. So you've got a many order magnitude gap between what a large language model requires and a machine on the wrist. So clearly we can't do that. We can't stream all the raw data to the cloud. We can't bring the large language model in locally. The good news is there's a better approach, a simpler approach, which is let the wearable device serve as an intelligent front end for the cloud-based large language model. I mean, the funny thing about the large language model is it's kind of dumb, right? All it knows is the data that we give it. It's got access to all kinds of interesting online data. It doesn't really have real world data. So it needs devices like this, or any number of the devices from the Internet of Things talked about earlier, to feed data up to the browser. And so that's the goal here. The goal is let's collect that 4 gigabytes of data, of raw data, and then let's run lightweight neural networks here locally that identify maybe 5 to 10 metrics of interest. So what's my resting heart rate? How much sleep am I getting? And then maybe 5 to 10 events of interest, right? So we talk in the embedded world about anomaly detection. So I'm going along, my voice sounds a certain way, and then one day I wake up and my voice sounds a little rattly like it does today. What's wrong? Oh, he's got allergies happening. Okay. So we want to identify change in behavior, change in state, and then send those up to the cloud. We then collect all this up. Maybe it's kilobytes or megabytes of data instead of gigabytes. We send it to a phone. That phone relays the data to a cloud. Now you've got that big cloud-based large language model sitting there. It can crunch all this data. It's got some knowledge of who I am and what my history is, and then it can make recommendations back. Say, hey Scott, I've noticed that over the last 3 weeks you've gotten 10% less sleep than normal. I'd like you to fix it. So we have the potential. We have all the technology pieces needed to build that mythical doctor plus personal trainer on wrist. So the question is though, how do you develop neural networks for a device like this? And this is a problem that Ambiq has been working to solve over the last 2 years, actually, quite acutely. And one of the outgrowths of that is something we call neural spot. And I'm not going to walk you through the entirety of this diagram. This comes from one of our data sheets. But neural spot is a set of software that can be combined with training frameworks like TensorFlow Lite or TensorFlow Lite Micro to design and train, network, and deploy it on our silicon. So on the left here, it's got a whole bunch of capabilities that allow us to design and train a network, allows you to iterate on that. And then once we've designed and trained that network, it allows us to map it efficiently to the Apollo SoC. There's a lot of talk lately about neural processing units, about NPUs that are these little neural engines capable of doing a ton of multiply accumulates in parallel. But the truth is, most networks that we want to run today aren't that big. They're pretty small, and they can run on a microcontroller very effectively. And so we've spent, of course, we have neural network acceleration hardware coming, but we've spent more of our effort on trying to figure out how to map these networks efficiently to the hardware. They don't tend to, when you just kind of pull them out of the box, they don't tend to map very well. And so we've had to do a lot of work to map that. And part of that has been building what we call our model suite. This is a series of pre-trained models that we provide open source training data, we provide the network itself, we provide weights, and it's basically an example code that you can use to go out and build your own neural networks. And I want to talk about two of them real quickly here to give you a sense for the complexity of that. Before I do that, though, I want to just reference one thing. There's a lot of talk in our world about metrics like TOPS per watt, so how many tera operations per 1 watt of power can be executed. And that's a really good metric. Understanding inference power is really important. It's a good metric, but it's only a small piece of the pie. So when you start looking at real use cases for our customers, what you find is only a small sliver of the total energy budget or the performance budget is actually being spent on inference. There's all this other stuff going on. There's sensing, there's pre-processing and storage of that data. There is OS that's running in the background. There's security software that's running. There's communications of that data elsewhere. And then there's all the the background stuff, like I've got to get energy from the battery down to my chip. You have to do all that really well. And that's what we're good at. And that's what the Spot platform is really well tuned for. So, we've got with our Apollo family and with all the neural Spot software running on top of it, we've got a complete solution that in the end is actually quite performant. And if you look at over a number of standard benchmarks, how we fare from an energy standpoint against other MCUs in that same category, we vastly outperform it. We consume far less energy for every inference that's run than the competition. And so I'll reemphasize something I said earlier, which is that this is only going to get better. And it's not just us, right? I'm going to kind of say negative things about our competition, but they're all working to make things better too, right? We're all seeing the benefits of Moore's law. Smaller transistors are better. They consume less energy. They run faster. They're better. They're more expensive, but they're better in some ways. We're seeing the introduction of new architectures like NPUs, which I talked about earlier. We're seeing sensor innovation, circuit innovation. Companies like Ambiq are continuing to drive power down for that whole AI solution. So it's going to be an interesting few years. And it's our job, or my job as CTO of this chip company, to be out ahead of the needs of our customers. So we talk to them today and say, hey, what do you want to use neural networks for? We're kind of, I don't know, we're figuring it out. Here's one use case. And we say, well, that use case is really lightweight. Doesn't justify all the hardware we're building. So what we're seeing now is a rapid change. They're adjusting rapidly to change the world. They're reading all the same AI papers that we are, and so they're very quickly catching up to how to use our hardware. That means we've got to kind of be out ahead of them as they develop. So I want to walk through two of the Model Zoo residents that we've created at Ambiq. First of those is something we call Heartrate. This is a series of neural networks that calculates heart rate variability, identifies arrhythmias, it classifies heartbeats. It's a multi-headed network that has a backbone that does segmentation of the ECG wave that's coming in. So it works with a front-end ECG sensor. It then has 3 upstream heads, 2 of which are based on neural networks and are looking at arrhythmias and are classifying beats. And then the third is basically just a set of conventional filters and signal processing that's looking at heart rate variability. And the idea is that this has the potential to be much higher accuracy than these hand-tuned algorithms that we would normally use in a system like this. It's been trained using open source data sets that we provide to customers. So I listed out some of them there. And the objective here is not actually to become a neural network development house. We're not equipped to do that. What we are equipped to do, though, is provide our customers with very clear, easy to use software examples they can use to go build their own. So I'm not trying to step on my customers' toes. I just want to give them something to run. Okay, and what comes out of this though is a lot of metrics that we can use to show them, hey, actually, inference on Apollo and inference at the endpoint is actually quite feasible. In this particular case, we've got Apollo 4 Plus evaluation board on the left. We have a sensor board on the right that's capable of doing PPG sensing as well as ECG sensing. And what we did is we built the Heartrate models on Apollo. We ran them, we analyzed them, just to give you a sense of how big they are. They're quite small. We're looking at a few tens of thousands of parameters. Think that each parameter is on the order of 1 byte. So you're looking at very, very small memory footprint. But what's great is you're getting high accuracy. So we're getting in the high 80s up to the high 90s for performance metrics. You know, any given customer might say, hey, that's not acceptable. I need it to be 99.9%. I say, fine, that's wonderful. Take this as a starting point, go modify your own model. And the more interesting thing here is, yes, the weights are relatively small, but we can run these in streaming mode. So it takes anywhere from 7 million to 20 million cycles per inference. And you can see the inference times there. That means I can run the streaming and I've got room left over to run all kinds of other models. So lightweight networks like this can be stacked up. We can run them on a chip like this the one running here on my wrist, and we can do so in real time. That's exciting. And I'm not the one who's going to solve that next wave of problems. It's going to be up to our customers to do. I want to give you another example. That last one was what I would call a streaming model. It's one that is running all the time. We have something we call sleep care. And this is something that identifies sleep stages, that identifies sleep apnea, sleep arousal, which is when you're kind of half waking up from sleep. And it is, again, it's meant to outperform little handcrafted algorithms that the customers use today. And we're seeing some very promising results. This one, disclaimer, is under active development right now. Our AI team is working on it as we speak. But it uses a whole bunch of modern techniques like separable convolutions, inverted residual bottlenecks, and all sorts of other stuff. So this is an interesting one, but it's one that runs relatively infrequently and requires almost nothing from a performance standpoint. But if you look at the metrics, they're I'm going to call them good, but modestly good. In fact, I just read a report today on how accurate the wearables are today with sleep. This is the one area where they're probably weakest. These wearables are incredible at heart rate variability and blood oxygen levels and all that. Not as good at detecting sleep stages, and we're relatively consistent with that. But optimization continues here. The more interesting thing is this: it takes tens of millions of cycles to do this, but that's per hour. Okay, when you look at in terms of the computational load that represents for a microprocessor at nearly 200 megahertz, that's like 0.002% of total system resource. I can pack many networks like this on a chip and swap them in and out of memory. So, you know, imagine I've got a big NAND flash chip on here. It stores 50 different neural network models. Those get pulled in once an hour. They get run. It assesses, hey, is Scott sleeping? Oh, okay, well, no, I'm going to put this away. Am I detecting that Scott is showing symptoms of Parkinson's? No, I'm going to put that model away. So you can get big coverage with a lot of models like this. So that's pretty cool. So what I envision here is that we're going to have a bunch of streaming models, and we work like hell to make sure that those streaming models are as small as possible because they soak up valuable resources. And then we've got periodic models like this that can stack that next. Look, my view is that the time for this preventative healthcare revolution is near, if not now. We don't want to do all that processing in the cloud. We don't want to do all the processing locally. There's this hybrid approach that it's actually quite effective. And there's been a lot of rapid progress. I showed you some peaks at progress via Ambiq. We've got good low power microprocessors. We've got very lightweight neural networks that are showing impressive performance. But there's a whole bunch of other companies like us that are out there doing things. So I'm optimistic about the potential here. And the pace of progress, as I said earlier, is staggering. Neural networks in particular are evolving so rapidly. And I would caution you against any company that comes out and says, I've come up with the perfect neural network accelerator. It's bogus, it's wrong, because these neural networks change so rapidly. Last week, they were all about, RNNs. This week, it's CNNs with some other modification on it. And I guarantee next week it's going to be different. So processors have to stay nimble. They have to stay flexible. I'm a big believer in building, faster, better, more energy efficient processors, but we've got to make sure that they can be flexible. Sure. I would say watch for really exciting developments from us, from our competitors. We have some new products that will be announced very soon that I'm particularly excited about that are going to really push things forward. And I guess my final comment is that I think preventative healthcare it's no longer a science problem. There are absolutely front-end problems, front-end sensing problems that need to be solved. We need to figure out how to reliably do non-invasive blood glucose sensing for one. But for the most part, it's an engineering problem at this point. There's a bunch of good technologies. The community has to work together to solve these things, and then somewhere out there, someone needs to solve that ecosystem problem so that insurance organizations and governments don't get in the way of us making this happen. So I'm excited, and I'm happy to answer any questions.
Thank you so much, Scott. So are there any questions? Then they So are there any questions? Maybe in the chat, Charlie, please.
Well, I like your takeaway that preventative health care is no longer a science problem. It's an engineering. I like that being in mind. The other issue I see is what I'll call hype. I recently saw a wearable that's supposed to be able to monitor my blood sugar levels. And if the cost hadn't been so much, I would have bought and seen. But there aren't, finding out how reliable, but there aren't any. How do you solve the hype problem?
Yeah, it's a good point, and I mean, to some extent, the market solves the hype problem, right? I mean, the best, if you look at all the top vendors, whether it's Fitbit or Garmin or I hate to even mention companies because then my customers get mad. But there's so many high quality ones that have hundreds of thousands and millions of users, and so I think the market solves it. I also see that there are traditional medical companies getting involved now. They're being held to a higher standard, right? When you don't go through FDA clearance, there is a big time hype problem. The market solves it, but it takes some time. When a company like Abbott comes in and has to go through FDA approval, that's a good thing. And what I've seen is some of the technologies that they've developed for, minimally invasive blood glucose tracking or lactate tracking for, say, diabetics, are being repurposed for athletes and the casual out there that need to play on the weekends. So I think we'll see a trickle down effect of the traditional medical technologies making their way to consumer areas, and it will be interesting for me to see does FDA start to take a strong role in regulating the Garments and the Fitbits. Certainly, there are features like ECG tracking that have gained FDA notice, but I'll be interested to see how it all plays out.
Any other questions?
Sure.
In the chat? Or no?
No,
Please go ahead.
let me do it directly. So, you put your finger on a couple of things that we see in the ecosystem. And one of them is, in fact, if you look at the number of accelerators, specialty AI chips, all of that, I find that there are at least hundreds of them at this point. Sort of a balkanization of the ecosystem in some sense. Okay? So how do you see a progression to actually solving that problem? Okay. And in a community way, figuring out how do we actually put something together that has that flexibility where I can abstract the specific neural network that I'm putting together, okay, and still be able to implement it.
Yeah, so I'm going to answer from the hardware guy's point of view. The better guy to answer this question is our VP of AI, and Carlos Morales. But from my hardware guy's point of view, I think it's vital to use standard architectures where possible. So we use ARM architectures today. We will have NPUs and future products that leverage standard architectures. We're not going out. There's been the temptation to go out and develop custom accelerators that do something really special. It's really, when given the pace of Moore's law, given the fact that I can drop voltage down and achieve low energy that way, and given that there's so much slack in the way that the network is designed, there was really no value in me going out really crazy on the accelerators. So my view is that on the hardware side, you'll see a few NPU architectures, a few accelerator architectures become standards, and companies like Google or ARM or whoever can kind of consolidate to them. So today, and then go ahead.
So I have sort of an analogy, and I'm curious how you view this. Glasser put together a fantastic book called Graphics Gems. Okay, and the value of Graphics Gems is in the 5 or 6 volumes, it had almost every graphics algorithm in there. Ray tracing, this, that, the other thing. Okay. That ended up being the requirements document for NVIDIA. Okay. And I wonder whether somebody is actually should put something similar for the AI world. Okay. Because what you find is most of the operations, if you have an open language like OpenCL as opposed to CUDA, there is no reason that you couldn't program, okay, whatever you wanted to actually do in terms of your, I would say, machine learning algorithms, essentially.
Yeah, it's an interesting idea. I don't, as a hardware guy, I don't have a good sense of how feasible it is, but I like it.
Yeah. Okay. Interesting.
Cool.
Interesting. Yeah.
Any question maybe in the chat?
I don't see any additional questions in the chat.
I would actually have a question. Just I'm a wireless systems person, so I did see that you're using physical energy on your Apollo chips. Any other communication technologies that you're using?
So we started with a focus on markets where short range matters and where Bluetooth is the standard. So in our case, we use low energy. You can expect to see Bluetooth Classic as well, so dual, but still near the cousin with that. Wi-Fi is a lot of places. If you were to open up a lot of our customers' products in smart home and wherever, you're going to find a Wi-Fi radio sitting next to it. So that's another one that's interesting. We don't have any products there. And then we also see a number of cellular radios. So I'm going to say that there's the intention of getting something like NBIT or one of these long range low power systems in there, but we are seeing like healthy radios.
Yeah. So Scott, in some sense, again, to take off on Jasmine's question. Okay.
Yes, and Adam, maybe you want to join us because actually next on our menu for today is the panel discussion of the speakers.
Okay.
So maybe you want to come up.
Sure. Yeah, we could do that. Okay. Yeah.
And then just follow up.
Yeah. No. So here is the question. Okay. If I look at what you're doing, and I look at the world of radios, most architectures, in fact, have a low end where you want to do your signal processing, and you want to compensate for any nonlinearities that happen in the amplifier at the low end. Okay. And I think from what you displayed, I don't understand why you cannot do that. That's number one, because it's a very similar problem to the ones that you're solving. The value, I would say, of actually being able to do this at the low end for something like LIGO, okay, where I have a much more complex setting, requires in some sense some degree of AI methods. Okay, to figure out how to do that cleanup at the low end and learn how to do it effectively. But it gives you one additional value if the power is low. And that is that I can now sort of drive all the antennas I have up there from a single computer. And understands how they interfere with each other, what talks to what, et cetera, et cetera. So I'm just sort of curious, how do you extend what you're doing in the product area, let's say in an area that you may not be much of a solution. Because, to me, it looks like a horizontal.
Yeah, I mean, I think what I'm hearing you say is that neural networks at an endpoint like this have a huge array of uses, one of which could be in communications. I agree with that. I'm particularly, one thing we've thought a lot about is codecs. So we've got a fixed width.
Yeah, 64 codecs out there, the very nice part. If I had something that ate less power to do codecs and adapt to them, so much the better. And there's a subtlety there, and that is in different parts of the world, people have different tonal habits, things of that sort. And you'd be able to personally adjust. So a person actually has their own, when we say their own codec, it's
Yeah, absolutely.
and not only that, in a consumer good that I would say fits what you're doing. If I were to look at, let's say, hearing aids, things of that sort, same problem. How do I really adapt that hearing aid to the capabilities of the person doing this?
Hearing aids is absolutely, I didn't mention this today, but it's probably one of the most interesting use cases where we see AI, IoT, and
All of those things come
Yeah, it's and I think that's where maybe some of the most amazing uses of AI will happen.
So that was more commentary than question, but
Oh, good. I like it.
the question it poses is how the hell do you march down the path where you have that kind of threat? And look, I mean, in some sense, when I look at it, the things that do best are what are called balanced computing. That may not solve all problems, but solves 80 to 90% of those problems.
Yeah.
And again, hides that complexity.
So what I'm wondering is that this is going, this question is going more in your direction. Scott, I know you specialize in digital, but you do need, the analog part of the RFIC and radio. Have you thinking about using kind of the software-defined radio or adaptive subsystems to, cover the needs of some of your customers?
Yeah, so first of all, let me just say that we do a lot of analog design, a lot of digital design. I would say that the thing that faces our customer most is the digital piece, right? It's the compute piece, but we do a lot of it. And from an RF standpoint, we have absolutely given thought to flexible and cognitive radios. It's not a step we've taken, right? I mean, to first order, what you will see from us is multi-protocol radios. So in the very near future, we'll have multi-protocol radios, but that's not that exciting. All we're really doing is we have one transceiver. It has relatively broad specs that allow us to serve multiple protocols, and then we've got a digital backend. So that's the extent of what we're doing right now. We haven't yet found the right use case for this.
Yes, I'm always thinking because with the digitalization that we have right now, one other thing that we have to take into account, every one of us, is the green transition. So it's not only the digital transition, and making everything possible that we can, or making every application happen that we can possibly serve, but to make it happen even in a sustainable way. And then I ask myself very often, so software-defined radios could help us a lot in dealing with all the technical challenges that we have, and maybe using various radios and serving various needs. But isn't it then too much of everything, of silicon, of power, just to have a sustainable solution there?
But I mean, if I were to look at, let's say, 5G radios, they're almost all something.
But 5G is never speaking about sustainability. Every
No, no.
communication person
The opposite.
never thinks about sustainability.
Just the opposite, they're power pots.
Yes.
That's-
I have this debate with myself all the time, right? I like to believe that we're green technology, we're low power technology, right? But I'd like to see the numbers to actually back that up, right? Are we actually having an effort? Yes, you could deploy our chips as part of sensors throughout this building to manage lights, turn them off, manage HVAC, whatever. We can certainly be green, but on balance, are we green? That's hard to say. I haven't done that analysis.
No, no. Definitely not.
Okay.
You know, especially in communication, no one is really, green yet.
Mhm.
But these software-defined radios would give us a means by reducing then tiny AI and tiny ML that we have on our devices that we showed it to really realize cognitive radios. But as cool as it sounds, I think it's not really sustainable from an environmental point of view.
I mean, the thing that interests me most is just sending less data, right? If we can find intelligent ways,
Reducing it makes a tremendous difference.
because you there's orders of magnitude.
No, it's sort of interesting because if you historically look at it. And it's actually sort of surprising because it goes back as far as the early 70s. Most of the more deep planetary space missions used to reduce their data on the ground. Okay, and because the most expensive part was the budget for transmitting it back to Earth. Okay.
But-
That was you had.
How to reduce the data? And by the way, so
Well-
people online, if you have any questions, please post them in the chat.
No, I think it's sort of more than a deep philosophical question. It's a very practical question because that trade-off between where do I store it, where do I compute, and where do I transmit it, okay, tells you what the right engineering equation is. Okay? And you have to do the trade-off. Now, I think from the example you put up, okay, it would be silly to have to transmit all of that data in a non-reduced form. Storing data is also expensive.
Yeah.
Why would you store something that you really don't need?
Definitely, but data we create like this.
Yeah.
Yes, but we create waste that way too. We waste 90% of the energy that we produce.
But there's fantastic ways to compress data, and we can use traditional compression algorithms, but we can also do things like, I love all this generative AI where you can say, paint me a picture of a dog holding a scepter, right? And it comes up with a painting and there it is. And so in a one short sentence, I've created this, thing that is probably a gigabyte worth of art, right? A couple hundred megabytes worth of art, right? So there are ways to compress data using neural networks that are exciting. And something like calculating heart rate variability, that is a compression methodology. That's taking all this raw data and compressing it down to one metric that I care about. And then the challenge in some of these cases is our analysis methodologies change, right? So as time goes on, we've got all this data on hundreds of millions of users of wearables out there. I want to use that data.
Curve fitting with exceptions and it's easy to figure out when you have exceptions. That's what it is.
Yeah.
Yeah.
Well, and I mean, when I, yeah.
Okay, I think we're probably at the top of the hour, so.
Oh, yes, yeah. Actually, not. We would have actually half an hour yet.
No.
But
2:30.
2:30. It's like 2 now. It's 2 p.m.
I think we should declare victory and go on break.
Yes, definitely. I would also say so. If there is not a question in the chat, then I say thank you for joining in. We'll start our session again at 3 p.m. Central. Happy to have you here. See you.
Okay, thanks.
Thank you. Okay, so Scott, I have a,
Thanks, Scott.
Oh, yeah, it was fun. So-
I have an offline. Let me see.